right, let's talk about the invisible glue holding tactical C4SAR systems together, mobile ad hoc networks, or MANETs. Welcome to this explainer. If you're building these systems, you know firsthand that the difference between mission success and complete radio silence usually comes down to your mesh routing. Today, we're breaking down the ultimate mesh routing battle. Let's jump right into our evaluation. We are looking at 4 absolute heavyweights dictating the modern battlefield today. Specifically, we've got 3 software protocols and 1 hardware behemoth. Here's our flight path for today. First, we'll map out the tactical networking battlefield. Then, we dive into BATMAN-adv for Layer 2 bridging, check out OLSR for topology visibility, and explore Babel for high-mobility swarms. After that, we'll look at MN-MIMO's physical dominance, and finally, wrap it all up with the ultimate comparison matrix. Part 1. The Tactical Networking Battlefield, Software versus Hardware. To really get this, we have to divide our theater of operations into 2 totally distinct engineering camps. On one side, you've got software-defined network protocols. These live up at OSI Layers 2 and 3, running on standard Linux environments using off-the-shelf commercial Wi-Fi chips. They literally do not care about the underlying radio frequency, they're totally agnostic. But on the flip side, hardware-defined Waveform Fabrics. These guys bake the routing straight into the physical layer, layers 1 and 2, using highly specialized FPGAs and custom RF transceivers. It's a completely different beast. Moving on to Part 2, BATMAN-adv, and the magic of Layer 2 bridging. So let's open the dossier on our first software protocol, BATMAN-adv. This one operates purely at Layer 2, and what that means for you in the field is that it entirely bypasses traditional IP routing overhead. Instead, it acts like a massive virtual Layer 2 switch. It bridges all your participating nodes together so that your devices act exactly as if they're plugged into one single flat Ethernet switch. Pretty wild, right? Here's how it actually pulls this off. Instead of forcing every single node to calculate and memorize a map of the entire network maze, BATMAN-adv keeps it incredibly simple. Nodes just periodically ping out these tiny originator messages. Their neighbors listen in, measure the packet loss to figure out the transmission quality, and then, here's the kicker, they only memorize the absolute best immediate next step toward the destination. No full route math required. Just, who do I hand this to right now? The tactical payoff here? Seamless land extension. It's totally plug and play. You get native support for multicast and ATAC data right out of the box, 0 crazy IP configuration needed. For a small to medium team, it's a dream. But there is a catch. Because it treats the mesh like a switch, broadcast frames, like ARC requests, flood the network. Once you push past, say, 50 to 100 nodes, you hit a massive scalability bottleneck. Plus, it's completely RF blind. It only sees packet loss, so it has no idea if that loss is from a physical wall or active signal jamming.
Let's pivot to Part 3, OSLR and topology visibility.
Shifting up to the network layer, Layer 3, we run into OLSR, which takes the exact opposite approach to BATMAN. Think of OLSR like an omniscient radar. It's a proactive link-state routing protocol. Its entire mission is to ensure every single node has a continuously updated, pre-calculated map of the whole battlefield at all times. Now, you might be thinking, wait, doesn't constantly updating a massive map just choke the network? And yeah, it absolutely would, if not for a really clever mathematical trick. OLSR restricts its control traffic to specialized nodes called multi-point relays, or MPRs. Only these designated MPRs are allowed to retransmit topology data, so the network stays clear and every node just runs Dijkstra's shortest path algorithm over the map to instantly know the best route. The massive advantage here is 0 route discovery delay. If a route exists, the node already knows it, period. It gives you highly predictable throughput, making it absolutely perfect for fixed or semi-mobile command post backhauls. But listen to me, do not put this on fast-moving assets. Seriously, it's a critical mistake. If your nodes move too fast, that MPR selection constantly breaks down. You'll end up flooding your RF channel with topology traffic, and your CPU and RAM usage will spike straight to 100%. Which brings us to Part 4, Babel, designed for high-mobility swarms. So what happens when you actually need high-speed movement? Enter Babel. Operating at Layer 3, Babel fuses traditional distance vector routing with strict mathematical feasibility conditions. This hybrid approach guarantees loop-free operations. Basically, it mathematically ensures your data won't endlessly run in circles, even when the network topology is completely chaotic and rapidly shifting. It manages this chaos because it tracks multiple routing metrics at the exact same time, things like expected transmission count and packet delay. It just adapts to degrading signals seamlessly on the fly. And by using destination sequenced numbers, it instantly invalidates stale routes. We're talking about rerouting packets in literal milliseconds when physical links break and reform. It is unbelievably fast. Tactically, this makes Babel an absolute powerhouse for high-speed UAV swarms or fast vehicular convoys. It even seamlessly integrates mixed wired and wireless topologies on the fly. But that agility, it definitely has a cost. Your engineers better know their stuff. Unlike Batman zero config setup, Babel demands rigorous Layer 3 IP subnetting. And fine-tuning those transmission metrics in a noisy RF environment, that requires some serious, deep expertise.
All right, part 5. MN-MIMO and the realm of physical dominance.
This is where we leave the standard open source software behind and bring out the big guns. MN-MIMO is a proprietary hardware waveform. Instead of running OS software over an abstracted network layer, MN-MIMO bakes the routing directly into the microsecond processing of the physical radio silicon itself, bridging layer 1 and layer 2 using an FPGA fabric tied to multi-channel RF transceivers. The physics going on here are just mind-blowing. It splits wide RF channels into hundreds of subcarriers using COFDM to just slice right through interference. Then, it applies space-time block coding and real-time eigenbeamforming across multiple antennas. But here's the actual magic trick. By exploiting multipath properties, this hardware literally turns physical obstacles like a concrete building or a cavern wall from a signal blocker into a signal amplifier. It gathers those reflections into coherent gain and routes data instantaneously based on raw physical metrics like spatial correlation and signal-to-noise ratio. Because of that incredibly deep physical layer integration, you get something open-source software on standard Wi-Fi chips just can't touch: an unrivaled 100 megabits per second throughput. Think about that for a second. That's enough pipe to push multiple real-time HD video feeds, voice comms, and telemetry, all simultaneously on a single tactical channel. If you're heading into contested environments, this spectrum dominance is just unparalleled. You're getting extreme electronic warfare resilience, massive anti-jamming overmatch, and low probability of intercept and detection. It's the absolute king of subterranean and urban non-line-of-sight environments. But obviously, you're locking into proprietary hardware to get it. You have to account for the intense size, weight, and power footprint, the swap, not to mention a drastically higher financial cost compared to slapping together some commercial boards. Finally, part 6, the ultimate matrix. Looking at the deployment metrics across the board, you can clearly trace the capability escalation. You've got BATMAN-adv giving you that seamless Layer 2 local bridging. Then you move to OLSR for highly stable fixed Layer 3 mapping. You scale up to Babel for those ultra-fast dynamic software swarms. And then, jumping straight to the top tier, you have MN-MIMO for pure military-grade spectrum dominance that completely shatters the commercial Wi-Fi hardware cap. So, as you go to architect your next C4 ISR deployment, you have to ask yourself a tough question. Is the raw, undeniable power and EW resilience of custom hardware silicon always the right tactical choice? Or does the flexibility, the low cost, and the rapid agility of open-source software swarms actually hold the true future of your operations? Something to chew on. Thanks for joining me on this explainer. Keep analyzing, and I'll see you on the next one.